It's my kids upstairs. They're making a racket. But it's summer vacation for them, so what are you going to do? All right, let's take a look at some problems. Question 18.18, we already covered the first one where we said, well, the electrophilic aromatic substitution is going to occur at this position. So I'm not going to spend any more time on that problem. So let's go on to the next one. So let's move on to B. You can see that we have a methyl group, and we know that a methyl group is a weak activator, and it activates to the ortho and para positions. Well, you see that this ortho position is blocked, and this para position is blocked. So the only place it can direct is here. And then we have the two nitro groups. Both of those are strong deactivators, but they both direct to the meta position. And the only meta position that's open is here. And thus, both of these groups are going to direct to this position. So this is where electrophilic aromatic substitution is going to occur. Let's move on to the next one. We've got three substituents on this guy. And if you look at those very carefully, let's start with the methyl group. We know that a methyl group is a weak activator. So we'll put here weak activator. And so it's going to direct to the ortho and or its ortho and para positions, which would be here and here. Of course, this position is blocked. And then there's something here that's a stronger activator, and that would be the ester. Right now, you might think, well, I thought an ester was electron withdrawing. No, if an ester is connected with the carbonyl directly attached to the aromatic ring, that is going to be a moderate deactivator. However, if you have the oxygen next to the ring, remember that you could show delocalization of those electrons in the ring. And so this ester is going to be a moderate activator. So it's the strongest activator in the entire ring, and it is going to activate to its ortho and para position. This ortho position is blocked, the para position is blocked, but this ortho position is open, and that happens to be meta to our moderate deactivator. So the moderate deactivator, this carbonyl, is going to direct to both of those positions. And so where is the electrophilic aromatic substitution going to occur? Well, it's going to occur where our strongest activator is directing, and so it will be at this position right here. We'll put EAS will occur here. Is everybody with me on that? Give me a thumbs up if you follow me on the rationale of those. Okay, well, the last compound has some symmetry in it. So I'm going to highlight these two carbons in green, and I'm going to highlight this carbon in yellow. Could anybody tell me, would the electrophilic aromatic substitution occur at the green positions or the yellow, where the yellow carbon is? Anybody have an idea about that? Yeah, absolutely. I think it's going to be where the green one is as well. If we go back to table 18.1, the nitrile doesn't come up a lot, but let's go all the way back to the table. Back to the table, where was it? Right here. And we saw that an alkyl group is a weak activator, and that a nitrile group is a moderate deactivator. So let's go back, that in mind. Let's find the question, which is somewhere down here. Okay, so the strongest activators are going to be the methyl groups. So we have a weak activator, which is going to direct to the ortho and para positions, ortho and para to that methyl group. So the ortho position to this methyl group, maybe I'll erase all these. The ortho position to this methyl group would be here and here. This position is blocked. And the ortho and para positions to this methyl group would be here and here. But again, this position is blocked. So these two carbons is where it's going to occur preferentially. And then since the nitrile is a moderate deactivator, it's going to direct to its meta positions, which would be here and here. And therefore, the electrophilic aromatic substitution is going to occur here or here, either one of those carbons, but it just asks for one position. And so there you go. We were able to look at all these compounds, and by using our knowledge of table 18.1, we were able to determine where electrophilic aromatic substitution would occur at each one of these compounds. Well, let's move on to question 18.20, which asks us something similar. Where is going to be the preferential site of electrophilic aromatic substitution on each one of these molecules? So we'll start out with 18.20A. Let's, kind of categorize these. Nitro, we have a strong deactivator. Then if we go to the methyl, let me use a different color. For the methyl, we've got a weak activator. Then if we go to the hydroxyl, we have a strong activator. And we know that the strong activator is going to determine where electrophilic aromatic substitution is going to occur. So let's just do it faster. This is going to direct to the para position, which is blocked, and its ortho positions. Now, if I highlight one of these ortho positions in yellow and one is green. Now, Lindsay, I'm just talking about ortho with respect to the hydroxyl, right? Could anybody tell me which one of these positions, and they're both ortho to the hydroxyl, there's no debating that. Which one of these, where would the electrophilic aromatic substitution occur based on what I taught you earlier, or what we went over earlier? Would it be at the green carbon or the yellow carbon? Anybody have a thought about that? Yeah, absolutely. Why would that be, Lindsay?
It's less sterically hindered.
Bada boom, bada bing. Beautiful. Love it. There you go. So it's going to preferentially occur here because, well, let's write it down. Less sterically hindered. I'm using abbreviations today. Good. Okay, let's move on to the next one. Could anybody tell me, let's try it a different way. We've got a nitro, we've got a bromine, and we've got a methoxy. Could anybody tell me which one of these is going to be the strongest activator? So it's going to dictate where the EAS will occur? Yes, yes. My students are on it, right? In it to win it, absolutely. So look, it's going to be the methoxy. We said it's what did we say it was? The strongest of the weak and the weakest of the strong. But anyhow, in the table, it's a moderate activator. Okay, we'll call it a strong moderate activator. Anyhow, whereas both of these are deactivators, so let's not even worry about those. So that means it's going to direct to the ortho and para positions. Its para position is blocked. Forget about that. We've got this ortho, and then we've got this ortho. Well, it's going to direct where the red carbon is because of the same reason that we saw before. The electrophilic aromatic substitution will occur here because it's less sterically hindered. All right. And what about the last one? Well, the last one has a plane of symmetry in it. I could label these carbons in red and these carbons in blue. Could anybody tell me where the electrophilic aromatic substitution, where they think it would occur? And this one you kind of got to put on your thinking cap a little bit. Nobody likes that expression, thinking cap. It's kind of a silly thing, but anybody have an idea about this one? We go to where the red carbons are.
I'm taking a guess, but is it the red?
I think you're right, Lindsay. That's what I would go for. Okay? Because they're both carbonyls, they're both meta-directors. There's no debating that. So the aldehyde is directing to where the blue carbons are, and then the ketone is directing to where the red carbons are. But you see, you've got this gigantic tert-butyl group. So this is an example where you can look at, even at the level of chemistry 3111, sometimes you can look at a compound and say, okay, both of these are deactivators. They're both moderate deactivators, but I mean, look at the size of this thing. This thing is gigantic. So even though you'd probably get a mixture, I would say, yes, it should preferentially occur here. And we'll say EAS, and the same thing we did the last two, less sterically hindered. That's just using a little bit of your knowledge of organic chemistry. And, as Dr. Oppenheim would say, it's organic chemistry. You can always go with sterics as a guess as to why the rationale. Let's take a look at this one, and then we'll get into some synthesis problems. This question just asks you, let's say, Nick and everybody else, let's say you wanted to take this compound. This is called isopropyl benzene, or you could call it cumene. And you wanted to make ortho-nitrocumene. So that would be a correct name. You could call it ortho-nitrocumene because it's a disubstituted compound. But would we need a blocking group to do this? Could anybody tell me? What do you think, based on what we learned? Yay. Will you give it a yay or a nay? Blocking group for this one. I would say yes, you would need a blocking group here because the isopropyl group is ortho-para-directing, isn't it? So that means it's going to direct to these two positions and the para position. But it's also a pretty big group, so it's preferentially going to direct to the para position. And so how do you get the nitro group ortho to the isopropyl group? What you would need to do is you would need to take the cumene. So let me just do some erasing here. So you would take cumene, and in the first step, you would treat it with fuming sulfuric acid. And that's going to install your sulfonic acid, which is a meta-director, but it's also your blocking group. So we have our sulfonic acid. Again, the sulfonic acid is going to direct to these positions, and the isopropyl group is going to direct to these positions. So everything is directing where we want it to, and thus, when we treat it with nitric acid and sulfuric acid to make our nitronium ion, we end up doing the nitration in the position that we want. So we get our nitro group installed here, and then we still have our sulfonic acid here. And then to make the final product, we would just treat it with dilute sulfuric acid, and that just knocks the sulfonic acid off. And so what about the last one, 18.22b? Would you need a blocking group for this one based on what we looked at or what we talked about? I would say, anybody have an idea?
No.
Yeah, I agree with you 100%. So we'll put a big old yes here and a big old no here. You do not need a blocking group for this, do you? Right, for B, all you need to do is just treat the compound with some bromine and some iron 3 bromide, and you are done, my friend. Why? Because this is so sterically hindering that it's just going to activate mostly to the para position. Or it's going to cause, I shouldn't say activate mostly, it's going to cause substitution to occur, preferentially at the para position. So there you go. Little practice on, table 18.1, activators, deactivators, little bit of tiny bit of synthesis practice, a little bit of blocking group practice. Well, with all that, let's move on. Yeah, go ahead.
A question about that. So what if you wanted it to go to the meta position? Could you block both ortho positions and the para position?
There's no way that I can think of, based on what we've looked at, to start with cumene and get the nitro group, or sorry, get the bromine in the meta position, because neither of these are meta directors, and so you'd have to do it through some other way.
So even if you block all the other positions, it just
yeah, if you had a whole holy host of different blocking groups, but the only blocking group that we cover in this class is the sulfonic acid.
Okay.
Oh yeah, there's other blocking groups that you could use for sure. I'm just trying to think, using our chemistry, how you would make, like if you wanted to make this compound, let's say you wanted to make this. You're getting ahead of me, Caitlin. So let's say you wanted to make this. I guess you could do a Friedel-Crafts acylation. So, you could make this compound first. You would install the acetyl group, and then, but that's a moderate deactivator. So then you could try to install the bromine. Then you could do what's called a Wittig reaction here, and then you could reduce it. So that's using some chemistry we haven't even learned yet, but that's probably the easiest way that I can think of. But I can't think of a way using what we know up to this point.
Okay.
Okay? So I will tell you right, in plain English, up to this point, we do not know everything that, is required to make every molecule out there. So we got a few good ideas for sure. And that brings us to this section right here. So a couple of things about this whole table here is we talked about bromination, chlorination, nitration a lot today. We talked about sulfonation, and we even talked about desulfonation, so going backwards, which is with dilute, H2SO4, H2SO4. What else? We talked about Friedel-Crafts, so Friedel-Crafts alkylation and acylation. Then we talked about the Clemmensen reduction, so Clemmensen reduction here. Now, and we also talked about the reduction of a nitro to an amine using iron or zinc. But, our book kind of tells us, and this comes directly from our textbook. He says, well, in section 17.6, and I've got my textbook open. If I just go into the table of contents here, just give me 2 shakes of a lamb's tail to look at section 17.6. Oh, good gravy. Come on, you. The textbook is not being kind to me. If you go into section 17.6, it's reactions at the benzylic position. So and it's also referred to here. So if you go into that section, he mentions benzylic bromination. Yes, it's covered, but he doesn't bring up this exact reaction. So what he talks about in section 17.6 is if you had toluene, for example, and you treated it with NBS, you would end up with bromobenzene. Or sorry, you would end up with, you'd end up with benzyl bromides, or you'd end up with this compound, okay? So all he's saying is you've still got 2 benzylic protons here. You've got this one and this one. And so if you treated it with excess NBS, like just piles and piles of it, then every hydrogen is going to be replaced by a bromine. So once you've got 3 bromines on there, then you've got a strong deactivator because you get so many bromines pulling electron density away. So that is something kind of old and kind of new, I would say. He doesn't directly have this reaction in the book, but it's kind of mentioned. And the second thing is for benzylic oxidation, the first reaction that he teaches you is not this one. He brings this one up as the second reaction, but the first reaction that he brings up for here, so I'm going to put a blue arrow here because I'm kind of running out of space. But the first reaction that he brings up is to use sodium dichromate, sulfuric acid, and water. And a student asked me a really good question. The student said, well, why do you learn these 2 reaction conditions? The reason why is if you use potassium permanganate as your oxidizing agent, that is done in basic conditions. So it's not acidic at all. And you only have to use mild acid to protonate the carboxylate. So you end up making the conjugate base of the acid, and then in step 2, you protonate it. Okay. Whereas if you use sodium dichromate, that's obviously very strongly acidic conditions. And so depending on whether your substrate had a group that's labile to acid or base, you would choose the appropriate oxidation method. Cool? So that's why you have both of those methods of benzylic oxidation. So that kind of covers these 2 reactions, which are they're covered in the book, but I'd say this one, he kind of didn't really say excess NBS will give you exhaustive bromination at the benzylic position, but now you know. And so synthesis strategies, what's a recurring theme in this class? Well, there's many of them, exceptions, but there's also, you get fire hosed with a million different reactions, and then you talk about how would you use them to make something. And Caitlin just brought up, well, what if you had 2 groups that are, meta-substituted? You have something here that's an ortho-para director, and then you have something here that's a meta-director. So what does that tell you? It means that you'd have to put in the nitro first. If you put in the bromine first, then your nitration would occur at the the ortho and para positions. Whereas if we install this first, we put the nitro in first, then we end up with the bromo at the meta position. And so that's the kind of rationale you want to have when you're tackling synthesis problems. It involves some serious retrosynthesis and being, pretty rock solid in your chemistry. And this is an interesting table. I never saw this. I usually remember everything that I saw when I was an undergrad, at least in organic chemistry. And this is a table I never saw, but I remember the first time I saw this in this textbook, I thought, that's a pretty cool table. What he does here is he shows you, here are some quick ways to convert a meta-director to an ortho-para-director or vice versa. Say, for example, we take a nitro group. Well, I taught you that you can reduce that using zinc or iron and hydrochloric acid. And you can make aniline, but aniline is an ortho-para-director. Why? Because it's got a lone pair, directly on the nitrogen. Okay. What else? If you did a Friedel-Crafts acylation, you have an acyl group. Well, that's a meta-director. You could do a Clemenson reduction. So again, this is the Clemenson reduction. So we'll put here reduction. And then you end up with an alkyl group, which is an ortho-para-director. And turning it around the other way, if you have toluene, well, a methyl group is an ortho-para-director, but if you oxidize it to a carboxyl group, that's a meta-director, right? And of course, we'll put here or sodium dichromate, sulfuric acid, H2SO4, and water. And then the last one, of course, if you take toluene and you do exhaustive benzylic or halogenation at the benzylic position, you end up with this compound, and it is also a meta-director. So these are just some, it's not an FYI table because these are all things that we covered. It's more of a check it out table. You can go from this to this, and you might want to use these thought processes if you're trying to make a compound like this one here. Let's say I asked you on a quiz, how would you make this compound? Well, shoot, they're both ortho-para-directing. An amino group is ortho-para-directing, and so is a chlorine. However, if you think in terms of retrosynthesis, if you had a nitro group here instead of an amino group, well, a nitro group is meta-directing. Can we make an amino group from a nitro group? Yeah, sure. Right, it says right here, you can take a nitro and just treat it with iron or zinc, hydrochloric acid in the first step. Second step, treat it with a little bit of base. You take the anilinium and convert it into aniline, and there you go. You can do that. So what does that mean? It means you'd want to start by making nitrobenzene. Now, if you were to take that nitrobenzene and do that reduction right away, now you're in trouble because you had the meta-director installed, and now you've taken it and kind of done the wrong thing because now you've got something that's going to put that bromine in the wrong position. And so, there's nothing wrong with this reaction, but if you're trying to make this product, that would be the wrong approach. What you need to do is you would need to do the nitration in the first step, and then you would need to do the halogenation before you do the reduction, followed by basic workup. Give me a thumbs up if you follow me on the rationale for just this one synthesis. If you have a question, don't hesitate to stop me. If you're just, why did they do it in that order? Why would you do it that way? Now, are you ready for this? Now, let's just back up. I want to get some things straight in your mind. It's nice to kind of go back and sort things out. If you remember, when we talked about dye-substituted compounds, I showed you 3 kind of exceptions for multiple substituents. Para product will predominate. Then I said if you have a 1,4, it's going to go with the less sterically hindered site. And then I said if you have 1,3, you almost never get any electrophilic aromatic substitution in the middle. Okay, so that was with dye-substituted rings. Now we're going to talk about some limitations of synthesis. So we're going to go down here and we're going to talk about limitations to synthesis. So you could call this, limitations to synthesis. We learned all these reactions, but there are a few caveats to some of these reactions. I know it can get annoying to memorize them, and especially when you think you've got a synthesis and you're like, this is going to be great. Then you look at the solutions manual, like, dang it, But I can tell you from firsthand experience that, when you work as a synthetic chemist, you find that out the hard way because you can't go to the solutions manual. That's really a cold condolence. But anyhow, first one is this. If you try to do nitration reaction on some kind of ring that already contains an amino group, it doesn't work. Okay, you can't do that. The reason why is that the amine can be oxidized by the nitric acid and sulfuric acid. There is a workaround for that where you can protect the amine. You can actually convert it into an amide. Jeepers, it's not really that important because it's not even covered in this chapter. But you can take this and you can convert it into an amide, and then it goes from being a strong activator um, to a moderate activator, and it's less basic, and therefore it doesn't react. But this is something that isn't covered, I think, until chapter 20. So don't even worry about that. That's not going to come up on your quiz. No way. We've got enough to worry about already. So that's the first one. You can't do a nitration on a ring that's got an amine on it. And the second one deals with Friedel-Crafts. Okay, Friedel-Crafts isn't the most robust thing out there. Like you can't just go around and do Friedel-Crafts like Friedel-Crafts for you and Oprah's giveaways. You get a Friedel-Crafts, you get one. Friedel-Crafts, you really got to examine your substrate whenever you want to try it. Okay, so just think of Oprah and her giveaway, and she would never give away Friedel-Crafts reactions because they're dicey or they don't work. If you have a moderate or a strong deactivator, Friedel-Crafts is just out of the question. Whether it's alkylation or acylation, it doesn't work. Okay, in order to do a Friedel-Crafts, you've got to have some activation, some kind, strong, moderate, or weak. Or if you do have a deactivator, it's got to be weak, like a halogen. Then you can do a Friedel-Crafts. But if you've got some kind of like acyl group or nitro, something like that, Friedel-Crafts will not work. It just doesn't work. So anything strong or moderately deactivating, Friedel-Crafts just doesn't cut the mustard. Okay, there you go. So they're like Friedel-Crafts. No wonder they didn't want to win a Nobel Prize. It didn't even work half the time. Well, that's not necessarily true, but anyhow, let's take a look at some problems here. It says starting with benzene. So we went to Target. They were having a fire sale. You know, when you first walk into Target and they have those little bins with stuff for $2 or $3, there was some benzene in there. So you decided to buy some. Starting with benzene and any other reagents of your choice, design a synthesis for some compounds here. Just so I have enough room, I'm going to go over to a blank document here. Let's see. Some stuff we did last class. We were talking about Friedel-Crafts. So this is question, what is it? 18.26. 18.26. And we're starting with question A. And we want to take benzene. Now let me draw it the way they have it. So they have it in this orientation. So you want to take benzene and you want to somehow make this compound. What would you call that, Lindsay? I'd call it orthobromoaniline, right? Would be a correct name, orthobromoaniline. Okay, let's see here. You've got two groups and they're ortho to each other. Not the easiest thing in the world to do, is it? Because you've got you get two groups that are ortho to each other. So that means you're going to have to employ a blocking group at some point. And we know that the only way that we know to have an amino group on an aromatic ring is to make it from a nitro. So we know that this is going to come from a nitro at some point along the way, so NO2, and that we're just going to have to reduce it. So if we had an NO2 group, well, that's a meta-director, but a bromine is an orthopara-director. So let's put here, bromine orthopara-directing, and a nitro is a meta-director. So that means if we want to have, like, if you think about this, if we could somehow make this compound where we have a nitro here, and then we have a bromine here, all we'd have to do is reduce it using, excuse me, iron or zinc and HCl, and then do a basic workup, right? So we could do that. So then the question becomes, well, how the hell do you make this? Well, again, the bromine is orthopara-directing, and the nitro is meta-directing. So you need to put the bromine in first. So let's imagine if you took benzene and you brominated it. So you use bromine, iron 3 bromide, you end up with bromobenzene. That's good. Nothing wrong with that. You know, and then you try to do nitration. Let's say you treated it with nitric acid and sulfuric acid. I mean, except for toluene, we said that any kind of activator is going to preferentially going to give you nitration in the para position. So what you'd actually end up with would be mostly this, where you'd have the bromine here and the nitro here. So that doesn't really help us. That would not be the best. Again, toluene is the only exception here. So could anybody tell me, what would be a strategy I might want to do here? I think I might have mentioned it. I think it might have slipped out of my mouth. But what would be my strategy here so that I could actually get that nitro group ortho to the bromine? Anybody have an idea? A strategy you might want to take?
You could use a blocking group.
Heck yeah, blocking group. That's what I think. All right, because if you treat this with fuming sulfuric acid, we end up putting the sulfonic acid para to the bromine. So now we end up with this, and we have our sulfonic acid over here. And what do we know? The bromine is directing to these positions, and the sulfonic acid is also directing here. So if we try to put that nitro group in, it's going to be in the right spot. So I'm kind of running out of space here. I'm going to make some more room for myself here. So what are we going to do? We're going to do the nitration. So we're going to need nitric acid and sulfuric acid. And that's going to give us this compound where we have our bromine. Now we've got our nitro group. And now we've got our sulfonic acid. Now we can see daylight because all we need to do is remove the blocking group and reduce the nitro. So let's start by removing the blocking group. So we'll use dilute sulfuric acid. And it gives us the ortho-substituted compound. So we're getting very close. Get our bromine here, our nitro here, and then in the last step, we're just going to reduce it. First step is to use iron and HCl, or you could use zinc and HCl. And then in the second step, we're going to treat that with sodium hydroxide, and that is going to give us the desired product, ortho-bromo aniline. So now we've reduced this to our amine, and there you have it. So how many total steps do we have? Yeah, go ahead.
Sorry, I just got a little bit confused. So I was with you up until we take the blocking group off, and then we're using dilute H2SO4. So is there, why did you choose the order that you did? Could you flip those? And would you be okay? No, you can't. So you have to.
Oh, you mean could you do the reduction first and then knock off the blocking group?
Yeah.
I suppose. But my rationale is this, is that, this is just treating the molecule with dilute sulfuric acid, just to pop that off. Whereas if I start trying to do a reduction with the sulfonic acid, there could be some kind of, hoobajoob that might happen there. And so if you, as a student, were to write the reduction first and then the removal of the blocking group last, I would give you 100%. But based on my experience, and if you're like, well, the hell with your experience, I don't have a graduate degree in organic chemistry, man, what do you expect? Well, again, if you wrote it in reverse order, I would say there's nothing wrong with it at all. So, yeah, Lindsay, I'd say either way would work. Does that help?
I mean, yes, I would like to develop a rationale for
yeah. I mean,
the understanding of it.
Yeah. There's nothing that we've gone over that I can think of that would prevent you from reversing it. So either way would be right.
Okay. Yeah. Thank you.
Either way would be right. I like to try to remove any kind of protecting group or blocking group as soon as possible to get that out of there. But there we go. And I mean, that's a 6-step synthesis, my friends. Bromination, sulfonation, nitration, removal of the solvent, so desulfonation, and then reduction and then a basic workup. 6 steps. Let's try another one. Let's see here. So same question. 18.26. Is this a great way to spend a Friday afternoon in the summer or what? Good thing the weather isn't all that great. I think this one might be an order of magnitude simpler. So if we want to put, so what would you call this? Metanitrochlorobenzene. son of a gun, why am I drawing that? I wanted to start with benzene, and then I want to make that compound. There we go. Take this, and we want to make metachloro nitrobenzene. I'm just going to throw this out there to my students because my students are great at synthesis. I think this one is going to be a little simpler. Which one of these groups would you install first? Would you put the nitro or the chlorine? And I can tell you there's only one right answer.
Nitro.
Absolutely, right? Because if you put the chlorine in, that's going to direct to the ortho and para positions. But remember, these are meta to each other. And so we've got to put the nitro in first. That means we're going to take our benzene and we're going to do a nitration. What are the conditions for nitration? You got to have them up in the old human brain. So nitric acid, sulfuric acid, go to the cupboard, grab both of those, and you do a nitration. You make that nitronium ion. The aromatic ring does a nucleophilic attack. Then you have the sigma complex. You do a proton transfer, and you end up with nitrobenzene. Now, to get to the final product, all you got to do is a chlorination. You could use chlorine and iron 3 chloride, but you could also use chlorine and aluminum chloride. That will work too. And that's it. So that's a two-step reaction, a little bit simpler than the first one. Let's try one more. Did I have any others? Oh, geez, I did have some others. Why don't we try one more? We'll skip 18.28 for today. We'll see if we have time to do it on Monday, because I do want to cover the last two sections with you today, the whole part about SNAR and elimination additions. Let's try one more. Let's see here. So this is 18.26. D. No, this is C. All right. So it's this compound. So we want to take benzene and we want to make an aniline derivative where we have the amino group over here, and then we have a propyl group. So 1, 2, 3, like that. Okay. So let's see here. We've got an ortho-para director here, and we've got another ortho-para director over there. Now, what did we say in terms of how do we add an amino group? The only way that we know how to do that is by nitration. That means at some point we're going to have some kind of nitrobenzene derivative in there. And then in terms of adding a propyl group, the only way that we know how to do that is by doing an acylation. Now, if you're thinking, why can't I just do a Friedel-Crafts alkylation? Because in that case, you'd get the carbocation rearranging, and you'd end up with a mixture of the propyl and isopropyl. So we'd want to go through the acyl group, and then we would want to reduce that using a Clemmensen reduction. Wow. So let's see here. What else? The Friedel-Crafts. We're going to have to do a Friedel-Crafts. And we know that Friedel-Crafts doesn't work if we have an electron withdrawing group on the ring. So what's going to be our mode of attack here? Does anybody have an idea of where we could start here?
I have a question.
Yeah, go ahead.
I don't know. I'm just trying to look at other things, but if we just started with NH2 without using the nitro, could you do that? Because it's an ortho-para.
So I'm not sure what you're saying. So you're saying you're starting with...
So maybe you start with the nitro, so you do HNO3 and H2SO4 right away, and then you make it the amine right away.
Okay, so then we take this and we convert it into aniline. Is that what you're saying?
Yes. Okay. And then it directs ortho-para, so then you could do the Friedel-Crafts, maybe?
Okay. All right. Something that I would say though is that this isn't very sterically bulky, and the amino group is really highly activating. So very highly activating. So whenever you have something that's really highly activating, like a methoxy group or an amino group, something that's got a lone pair on here. So this is a strong, strong activator. Then, I wouldn't choose to put that in first, because then if you try to do the Friedel-Crafts reaction, you could get polyacylation. Now, again, in our book, or yeah, in our slides and in our textbook, he says, well, I assume that you get monoalkylation. So yeah, I would say that you could do that first. You could take this, and then you could do the Friedel-Crafts. So then you could install the acyl group like this, right? So you do the Friedel-Crafts acylation, and then you could just reduce it like that. Okay, I wouldn't say that there's anything technically wrong with that, but if you look in the textbook, I'm pretty sure that's not the way that he would do it, because if you install the propyl group first, it's more sterically hindering, so it's going to force things, preferentially into the para position versus the ortho position, and it's a weak activator, and so you're not going to get any kind of polynitration or anything like that. So I would say there's nothing wrong with the order of events that we have here, but I would say preferentially you'd want to do the Friedel-Crafts chemistry first on the aromatic ring. Does that make sense?
It does, yeah.
Yeah, yeah. Again, I would accept either one. I don't think there's anything wrong with this order of events. But again, I haven't looked at the solutions manual. I have my notes here in front of me. But my guess is that you'd want to install the propyl group first. And let me just show you why. Okay, so picture's worth 1,000 words. The thing is, if you make the strong activator, you can get polyalkylation, acylation, bromination, what have you. However, if you did the Friedel-Crafts first, so let's take this acid chloride that has 3 carbons in it. We have aluminum chloride. Then that's going to give us this compound. So we have our ketone. Then we can do our Clemmensen reduction. I'm probably going to run out of space here. So our zinc mercury amalgam with HCl, and then we heat that up. And that's going to give you the propyl group. So the propyl group will, number one, it's going to prevent polysubstitution because it's not a strong activator. It's a weak activator. And also, it's just so dang big that when it's kind of flopping around like a flag in the breeze, so to speak, it's going to make sure that the 2 ortho positions are blocked, and it's going to cause preferential nitration at the para position. So now when we take this and we treat it with nitric acid and sulfuric acid, we're going to exclusively get, the para substitution product. So we end up with this, and then the last step is just reduction of the nitro. And this time, why don't we use zinc and HCl followed by treatment with sodium hydroxide, and that will give you the desired product. But again, Lindsay, if you go all the way back to chapter 11, first chapter we did in this class, and the last chapter that we do in Organic Chemistry 1, our book says that when you're studying with friends, sometimes you'll both run into answers and you're both right. And again, I would say that I would accept your order of events, but I think this would be a better approach. But again, I would give both of them 100% if a student wrote them down as a synthesis. All right. And why don't we skip question 18.28 for now, and we'll get into some SNAR chemistry. What time is it? There we go. Back to the slides. Back to the shack, Jack. Where were we? Somewhere around here. We talked about this already. Did this. Done all kinds of cool stuff today. Well, I know that everybody's probably tired, and that's totally normal. It's Friday afternoon. But let's cover the last couple sections. Good news is that they're a lot shorter than everything else. So it won't take us a lot of time to go over it. And I can tell you something that I bet will pique your interest, is that my students love to know what kind of questions show up on ACS finals and MCATs and DAT exams. And I mentioned this earlier today. that section 18.13, which is nucleophilic aromatic substitution, we call this SNAR chemistry. The ACS final they love this reaction. You know, Dr. Diaz's sister was studying for the data a number of summers ago, and I was going over some of the review materials that she had. They love to ask this. So very important chemistry, SNAR chemistry. And the good news is, if you understand everything up to this point, and I'm pretty sure my students are rock solid on the whole sigma complex, then you're going to understand how now our aromatic ring, rather than acting as a nucleophile, it acts as an electrophile. Because check this reaction out. We have paranitro bromobenzene, and then we're treating it with sodium hydroxide at 70 degrees, and we end up with paranitrophenol. Well, what in the heck is going on here? How is this happening? We've got a strong electron withdrawing group on the ring here. You're only taking sodium hydroxide 70 degrees. That's not that warm, okay? And somehow you're adding a hydroxyl group on here. Well, we know that hydroxyl is a nucleophile, right? It's definitely not an electrophile. There's no electrophile in these reagents. So where's the electrophile? The electrophile must be the ring. And that is our electrophile. So here, the hydroxyl group acts as our nucleophile, and the bromine acts as a leaving group. Well, check this out. An SNAR reaction, really neat reaction. In order for this kind of reaction to happen, this SNAR reaction, there's three things you got to look for. Number one, the benzene ring has to have some kind of strong electron withdrawing group. Checkaroo, got a nitro group. In fact, in this class, I'll just write down here, it's usually, not always, but usually a nitro group, NO2 group. I'd say the vast majority of the time. The group has to have a good leaving group, or the ring has to have a good leaving group. A checkaroo for that. Bromide, conjugate base of a strong acid, great leaving group. Chlorine, bromine, iodine, all good leaving groups, so we got that. And then the leaving group has to be positioned ortho or para to the withdrawing group. We'll check it out. If I just redraw that molecule, our leaving group, our bromine, was para to the nitro group. So we would also see a similar reaction if we had the bromine ortho to the nitro group. We'd still see the SNAR chemistry. If the leaving group was meta to the electron withdrawing group, you get nothing. No reaction. Zilch. Doesn't work. And this, again, is something they love to ask on those standardized exams. Well, you remember that sigma complex where we had that positive charge delocalized throughout the aromatic ring? Well, now that we've got an electron withdrawing group in the meta position, that nitro group, when we look at the intermediate that's formed, it's called a Meisenheimer complex. And when the nitro group is in the meta position, it's unable to stabilize the Meisenheimer complex. Now, if you're like, what the heck is a Meisenheimer complex, Mr. Dion? Well, let me show you. Let me show you right here on this slide. First step, a nucleophilic attack. Haven't seen that before? No, I've seen that a million times, right? The first step is a nucleophilic attack. Let me just zoom in here. A hydroxide is a dandy nucleophile that came from our sodium hydroxide. But check out these arrows. You get it attacking this sp2 hybridized carbon, which is our electrophilic species. And then you have the electron density being poured into the ring. And that is the Meisenheimer complex. When you draw all the resonance contributors that show the negative charge delocalized throughout the ring, this is our Meisenheimer complex. But why does that nitro group have to be either in the para or the ortho position? It's because when it's in the ortho or para position, we get one extra resonance contributor where we have the negative charge delocalized all the way down to the oxygen of the nitro group. So we would see this occurs with ortho too. But if you try to draw the Meisenheimer complex that results from meta nucleophilic attack, you cannot draw this resonance structure. Now I got one for you. Is anybody here a fan of wrestling, like WWE or WWF from the 90s or 80s or whatever? Anyhow, sometimes there's a move that wrestlers do where they'll run across the ring and then they bounce off the ropes. I'm actually acting it out in my office right now. They'll bounce off the ropes and then they come back and then they'll give somebody a clothesline or something. Well, that's kind of what's happening here, right? You have the electrons going all the way down into the ring and then poof, they come back out. And when they come back out with all these arrows, 1, 2, 3, you end up ejecting the chloride as a leaving group like that. And that's what I always think about. Maybe we call this the WWE mechanism or something. I'm not a big wrestling fan, but I know, rebounding off the ropes. Is anybody with me on that? Maybe not. Anyhow, yeah. So there you go. And that's the mechanism of an SNAR. And this intermediate that has a negative charge delocalized throughout the ring is what we call a Meisenheimer complex. So what do we need the acid for? Well, you can imagine that if you're making a phenol and you're in base, well, if you had the hydrogen here, you've still got more hydroxide. It's going to rip that proton off like stink. Okay, and so what do you need? You need some acid. So the first step is to treat it with excess sodium hydroxide, cook it up a little bit, and then the only way to isolate the phenol is to treat it with some acid in the second step. All right. And this is one of the few ways that we know to make a phenol, right? This is a phenol. And if you think about how many ways did we learn how to make a phenol? We haven't, except for acidic cleavage of an ether. This is the only way that we know how to make a bond between an oxygen and an aromatic ring. So if you see a bond between an oxygen and an aromatic ring and you don't have one in your starting material, you are going to have to think about SNAR chemistry. Let's take a look. Predict the product of the following reaction. What do we got here? We've got this compound. We've got a chlorine. We've got a bromine. We've got a strong electron withdrawing group. And we've got sodium methoxide, right? Let's draw the Lewis structure. Sodium, or the partial Lewis structure, I guess. Sodium methoxide. This is a great nucleophile. Which one of these halogens is going to act as my leaving group? Would it be the chlorine or the bromine? Can anybody answer that? And again, there's no trick questions. Who would be my leaving group for my SNAR reaction? Chlorine or bromine? Yes, absolutely. It's the chlorine. Why? Because it's para-substituted. So what's going to happen? Let me show you how I like to draw the mechanism. So I'm going to redraw the substrate. So just bear with me for a second. You know what? Maybe I'll just draw it down here. Here's how I like to draw the mechanism. I'm the instructor. I don't have to draw every intermediate of the Meisenheimer complex. I need to practice that. But if we draw the entire nitro group, then we can draw that mechanism that shows the halogen being ejected. So here's my bromine. Here's my chlorine. And we know that our nucleophile is going to attack right here. Let me get my red pen. So our nucleophile is going to attack this carbon right here. What's going to happen? Those electrons are going to go all the way down to the nitro group. And we're going to end up with this intermediate where we have our methoxy group and our chlorine attached here. Now we've got the negative charge delocalized all the way down, way down into that nitro group. And now here we go. Here's the mechanism where we're going to lose that leaving group. So just like a wrestler rebounding off the ropes, we're going to make this new pi bond. We're going to regenerate the aromatic ring, and the chlorine is going to get lost like this. We'll put minus chloride, and then we end up with our product, which is going to look just like this. So let's put in our bonds. Nitro group. Oops, I forgot my bromine. Bromine is still here, so I've got my bromine here. And now I've got my methoxy group. And there you have it, my friends, an SNAR reaction. What were the requirements? Let's review. Number one, you've got to have a strong electron withdrawing group. Check. Number two, you've got to have a good, it's got to be, you've got to have a good leaving group. So number two, and then number three was that they have to be ortho or para to each other, and they are para to each other. And so this substrate makes a perfect substrate for an SNAR reaction. Yes, Nick, sorry, I got the bromine back in there at the end. I redeemed myself at the last second. So why don't we skip section or question 18.31, and we'll come back to this on Monday. You can try designing a synthesis for this compound, and you can see that we have a bond between an oxygen and a carbon, and it says you're starting with benzene. Therefore, this is going to require an SNAR reaction, right? Because the only way we know how to make an oxygen-hydrogen bond between an oxygen-carbon bond to an aromatic ring is from an SNAR. And so I want you to give this one a shot. We'll come back to it on Monday. But let's cover the very last section of chapter 18. I think this is the last section, except for just distinguishing between the different types of mechanisms. And this is elimination addition. Are you ready for something kind of crazy for your last section of the chapter? We're going to talk about this molecule that I told you about this last class. You have a triple bond incorporated into an aromatic ring like this. Oops, that's not very pretty. Something like this. We call this benzene. And I brought this up last class just to kind of throw it in your face and say, like, look at this crazy molecule, benzene. And you're probably thinking, Mr. Dion, you always told me that if you have a triple bond, that the bond angles should be 180 degrees. You know, so how in the heck do you have a triple bond incorporated into a six-membered ring? We're going to talk about that in just a second, but check this reaction out. If you take chlorobenzene and just treat it with sodium hydroxide and heat, like 70 degrees Celsius, for example, the conditions for the SNAR, nothing happens, right? Because you don't have an electron withdrawing group here or here. Zilch, zero. However, a lot of interesting chemistry can occur if you provide enough energy. And so if you crank this up to 350 degrees Celsius, I mean, that's super high temperature, you can end up making phenol that way. And, you know, when chemists first discovered this reaction, they were actually kind of confused about it. You know, they said, well, how the heck does this happen? And so what they did is some really interesting chemistry. They tried another reaction where they took chlorobenzene and they treated it with sodium amide, ammonia, and then followed by an acidic workup. And they found out that they got aniline. So they were also confused about that. So then they said, okay, well, what if we put a substituent para to the chloro? What would we get then? They found out that they get a mixture of para methylaniline and meta methylaniline. So they got two regioisomers in approximately a 1-to-1 ratio. So they get a 50-50 mixture of both of these. And said, what's going on here? How is this happening? It can't be an SNAR reaction. That's impossible, right? It can't be the amide is acting as a nucleophile and then you're getting an SNAR, because then how the heck would you end up with this product? And so this is not what it cannot be what's happening. Can't be that. And so they tried something else. So they tried using an isotopically labeled carbon substrate. When we see this little star here next to the carbon or the chlorine, this star means that it's carbon 14. So carbon 14 is the least abundant isotope of carbon, and that way they can monitor where that carbon, is in the final product. And they try the same reaction again, and they found out they get a 50-50 mixture of these two compounds, where you have the radiolabeled carbon or the carbon 14 next to the nitrogen, or one carbon away. Now, well, how the heck did that happen? And what they realized is this must be due to some kind of elimination reaction occurring first to form this intermediate that they call benzene, where you have a triple bond between two carbons in this six-membered ring. Right? Because if that happens, then that renders that triple bond susceptible to nucleophilic attack by amide, which is a good nucleophile. However, the amide, if I draw it like this, okay, amide like this, it could attack at this carbon. It could attack at this carbon, the radiolabeled carbon, or it could attack here, one or the other. And that's exactly what's happening. So the first step is an elimination. Let's write that down. This is an elimination reaction, right? We're eliminating HCl essentially. We make benzene, and then the benzene can undergo nucleophilic attack. And so this would be the addition step, right? We're adding the NH2 group to it. So we do a nucleophilic attack on the benzene, the first step, and then it's followed by a proton transfer where we have this negative charge on this carbon of our aromatic ring, which does deprotonation, and we end up with aniline. And we call this the elimination addition mechanism. Pretty crazy, huh? Pretty neat chemistry and elimination addition. Now, if we look at that mechanism in more detail, well, when we were talking about making the phenol, here's the mechanism of it. If you have a good leaving group, you treat it with your sodium hydroxide, and this is at very high temperature, at something like, what was it, 350 degrees Celsius. You do the elimination, you form benzene as an intermediate, and then the hydroxyl can come in and it can attack at this carbon or at this carbon. They just happen to show it attacking at the carbon in yellow. It's neither here nor there. And then we do a proton transfer and get the final product. Now, if you're going, what the heck? I still don't get this benzene thing. How could you stick a triple bond in a ring like that? There is actually some evidence that the benzene exists. If you put a little bit of furan, which is this compound right here, if you put a little bit of furan in some of these reactions, it will actually trap the benzene. It actually not traps the benzene, but it will react with the benzene in a Diels-Alder fashion to make this compound. And so that's proof that you end up with this benzene intermediate. Well, it still seems kind of wacky to me that you can end up with this thing. And so if you look at our textbook, he goes into a little bit more detail about the benzene. I'm not going to go into that today. I'm not saying it's not important, but it's something I'm not really going to ask you. But there's actually more evidence that the benzene might exist as a diradical. So it might actually look like this, where you have a double bond here, and then you have a radical here and a radical here. So it's like a diradical, and each one of those unpaired electrons is in an sp2 hybridized orbital. And you can imagine that the orbital overlap of those two sp2s coming together would be really inefficient. And so that's why benzene is so dang reactive. It's not very stable. But that's the bottom line of elimination addition. And so it says here, draw both of the products that are obtained when 4-chloro-2-methyltoluene is treated with sodium amide, followed by treatment with aqueous acid. So let's draw 4-chloro-2-methyltoluene. So why don't we draw toluene like this? I'll just put my methyl here. Then if we have a 4-chloro-2-methyl, so we'd have a chlorine here and we'd have a methyl here. And then what we're going to do is we're going to treat this with sodium amide. So we're going to use sodium amide in ammonia. And then in the second step, we're going to treat it with aqueous acid. So what's going to happen in the first step is you're going to get that elimination occurring. But we have, and I'm just going to erase the second step for now. We have a proton here, which we could use to do elimination, and we have a proton here that we could use to do an elimination. We could form either one of those intermediates where you remove the blue proton to make benzene or the red proton to make benzene. Now, if you were to remove the red proton to make benzene, so let me just use my black pen here. If we had the amide and we removed the red proton like this, then I end up with this intermediate. So I'm just going to draw the benzene intermediate like this. So we end up with the double bond here and here. And now my amide can come in and it can attack from either one of these carbons. It can attack at the green carbon or the yellow carbon. So my amide can attack at the green carbon, or they could attack at the yellow carbon. Now, I'm drawing two mechanisms at once, which isn't really correct, but I'll do it anyway. So if it attacked at the red carbon, after the aqueous workup, so I'll do this, and then I'll put H3O plus next, okay, you would end up with this compound where you have the two methyls here, aromatic ring, and then you have the amino group here. But if it attacked where I have the blue curved arrow, then in that case, you'd end up with this compound where you have aromatic ring, the two methyls, and the bromine right next door like that. Okay, so that's one possibility. However, besides those two compounds, let's take a look at what would happen if you removed this proton that I have in blue. So if you did the elimination, so we'll put here remove blue hydrogen, then you'd end up with the benzyne in a different position. Now, you'd have to shift the double bonds, meaning you'd have to move them all over one, but I'm just going to do that simultaneously. So you'd end up with this compound where you'd have the benzyne here and your two methyl groups here. Now your amide is going to come in as your nucleophile, followed by aqueous acid, and the amide could attack here, or it could attack here. But since this molecule has a plane of symmetry through it, this benzyne intermediate has a plane of symmetry, either way, you're going to get the same product. You're going to end up with this compound, so I'll just draw it out here quickly, where we have a double bond here, and we have our amino group here, like this. And hopefully you can see that this compound and this compound are identical. And therefore, what's the answer? What are the two products? We get the product that's in the yellow circles, and then because these two are the same, and then you would also end up with this region. Did I put the bromine in there when I meant to put a amino group? Mr. Dion, it is too late in the day. So you would get this regioisomer as well. So that's a little bit of elimination addition. Chemistry, proceed through a benzyne intermediate. And with all that in mind, that brings us to the very end of the chapter. And really, what did we cover in this chapter? Okay, what did we cover? Most of what we did was electrophilic aromatic substitution. You know, this is covering sections 18.1 to 18.12, really. That is the vast majority of the chapter, vast majority of it. Now, if we go to I'm in the wrong chapter here. If we go into the SNAR section, that is covered in section 18.13. So 18.13, a very short section on SNAR. And elimination addition is covered in section 18.14. And then this is section 18.15, which is really just making sense of all these. So how do you know what you're doing? Okay. Well, what you want to do is look at the reagents that you're dealing with. Okay. Are your reagents electrophiles or nucleophiles? If they're electrophiles, well, then it's going to be some kind of electrophilic aromatic substitution, bottom line. So electrophile, you're going to end up with an electrophilic reaction. If your reagents are a nucleophile, like a hydroxide, a methoxide, an amide, well, then those are all nucleophiles. They're definitely not electrophiles, that's for damn sure. So that means it's either an SNAR or an elimination addition reaction. If the criteria that you need for the SNAR reaction are there, if you have a good electron withdrawing group that is ortho or para to a good leaving group, then you're going to have an SNAR reaction. But if you don't have any of that, then it's going to be elimination addition. And that's the one that proceeds through the benzyne intermediate. And there's only a couple examples that we look at of that. All right. Well, that's all of the content of the entire chapter. That's the whole thing. And so I think that maybe we'll skip this one too. And these are all the reactions that we looked at in sections 18.1 to 18.12. Then we covered the section on SNAR. So again, I said that was section 18.13. And this is section 18.14. All right, here we go, 18.13 and 18.14, and that's the entire chapter. Big chapter, a lot of work in this chapter, there's no doubt about it. Nick, yes, I just noticed that at the end, but why don't we